Okay, so let's do a few examples of assigning oxidation numbers. So here are two compounds. One is called potassium permanganate. And potassium permanganate is KMNO4. And then there is potassium permanganate. Whoops, sorry, that's potassium permanganate. And then there's just potassium manganate, which is K2MnO4. So the oxidation numbers of potassium and oxygen are not going to change. But because manganese is a polyatomic ion, not polyatomic ion, it's a transition metal here in this D block of the periodic table, it can have multiple ionic charges, which means it can also have multiple oxidation numbers. So we are going to assign the oxidation number for manganese in both of these. We'll actually assign the oxidation number for all of them. So remember, the rule is that when you are looking at the both of these are compounds, which means the sum of the oxidation numbers has to equal 0. The ions, it has the charge of the ion. So for example, potassium is +1, so that means that this is going to have a oxidation number of 1. Oxygen is -2, so that means it's going to have a oxidation number of -2, but I have 4 of them. So let's just write it out. So I have 1 potassium plus however many manganese is. I have to do that one last. Plus 4 of the oxygen, which have a charge of -2, and all of this has to equal 0. So +1 plus something plus -8 equals 0. So that means that the oxidation number of manganese in this compound has to be +7, because +1 plus 7 plus -8 equals 0. So that means the oxidation number of manganese in potassium permanganate is +7. Let's see what the oxidation number of manganese is in potassium manganate. So again, potassium is +1, but now I have 2 of them. So 2 times +1 plus whatever manganese is, plus, and I still know oxygen is -2, I still have 4 of them, 4 times -2, now this equals 0. So now what is manganese in potassium manganate? Where 2 plus something plus -8 is 0. Well, that means manganese must be +6. So the oxidation number of manganese in potassium manganate is +6. In potassium permanganate, it is +7. So this is an example of assigning oxidation numbers in a compound where we have a transition metal that has multiple options for oxidation numbers. The reason that this is important is because when we start writing oxidation reduction half reactions, the oxidation numbers are going to change on other sides of the arrow, and we need to see if that number is increasing or decreasing to know if the electrons are being gained or lost, to assign it as either an oxidation or a reduction, which is why we have to be able to correctly assign oxidation numbers. So let's look at another example. Let's look at assigning an oxidation number in a polyatomic ion. So here's the dichromate ion. So the dichromate ion is Cr2O7, and it has a charge of 2-. So this is a polyatomic ion, which means the sum of the oxidation numbers is going to equal the charge on the ion. So up here, we wanted the sum of these oxidation numbers to equal 0 because these were neutral compounds. The charge on these compounds is 0. The charge on this polyatomic ion is -2. So that means I want the sum of all of these oxidation numbers to equal -2, not to equal 0. Well, chromium is also a transition metal, so it can have multiple ions, which means it can also have multiple oxidation numbers. So I don't know what the oxidation number of chromium is, but I do know what the oxidation number of oxygen is, so I can figure it out that way. So the oxidation number of oxygen is -2. So that means I have -2, and I have 7 of them. So 7 times -2, plus 2 times whatever the charge of chromium is. So 2 times something plus -14, 7 times -2 is -14, equals -2. So that means this term right here must be 12, because 12 plus -14 is -2. So this term right here has to be 12. So what times 2 is 12? 6. So that means this must be +6. So the oxidation number of chromium in this dichromate ion is +6. So again, the only difference here is that in this example, these were compounds, so we want the sum of the oxidation numbers to be 0. In this example, it's a polyatomic ion with a charge of -2, so we want the sum of the oxidation numbers to be -2. Let's look at one more example where we are determining what's being oxidized and what's being reduced in a chemical reaction. So I'm going to write out the equation. So it said solid zinc reacts with aqueous silver 1 to produce aqueous zinc 2 and solid silver. So we're going to write the reaction from this sentence and then assign oxidation numbers and then determine what's being oxidized and reduced. So I'm just going to write out the steps. So 1, we'll write the reaction. 2, we'll assign oxidation numbers. And then 3 will determine what's being oxidized and what's being reduced. Okay, so it says solid zinc, so that means zinc solid reacts with aqueous silver 1. Aqueous silver 1, this is the silver 1 ion. So it's reacting with it. So these are the reactants. Silver 1 aqueous. And then it says to produce, so that means there's my arrow, aqueous zinc 2. So that's the zinc 2 plus ion, aqueous. We know ions are aqueous, so that's a clue that these are ions. Ions are charged. Also, it tells you the number in Roman numerals of what the charge is. It produces aqueous zinc 2 and solid silver. Okay, so that's the equation. We just wrote it. So now we can assign oxidation numbers to all of the species, reactants, and products in this equation. Well, the rule says that atoms have an oxidation number of 0. So that means the oxidation number of zinc is 0. That also means the oxidation number of this solid silver is 0. The rule also says that the charge of a monatomic ion is the oxidation number. So that means the oxidation number of this silver 1 is +1, and the oxidation number of this zinc 2 is +2. So now what we're going to do, we've assigned oxidation numbers to this reaction. The next step here would be to write the half reactions and see what's happening. So this is kind of like conjugate acid-base pairs when there's just a transfer of a hydrogen, except instead of transferring hydrogens, we're transferring electrons. So you're seeing what is the same on opposite sides of the arrow, only differing by the number of electrons. So the pair here would be the zinc 2 and the zinc 2 plus, and then here would be the silver 1 and the solid silver. So now we're going to be able to determine if something is being oxidized or reduced, because remember, an oxidation number loses electrons, the oxidation number increases. A reduction reaction gains electrons, and the oxidation number reduces. So let's see what's happening here between the zinc solid and the zinc 2 plus. The oxidation number is increasing. Half reactions where oxidation numbers increase means that this is an oxidation reaction from zinc to zinc 2 plus. And over here, from silver +1 to 0, the oxidation number is reducing. It's going from +1 to 0. So this would be the reduction half reaction. So this is why assigning oxidation numbers is important, because we ultimately need to be able to assign oxidation and reduction half reactions. We're going to do a lot more examples of this, but these are just some examples of how we assign oxidation numbers to different pieces of compounds or polyatomic ions, or even just this equation right here.